everybody. This is the second year of the Rust Development Forum. Thank you for joining us. These are our first speakers. They're going to tell us about RustPython. So a warm round of applause to Windel and Shin.
All right. So congratulations for getting up this morning. That's an achievement. So welcome to this talk. So what we will present is who we are, what is Python, what is Rust, what is RustPython, and hopefully give some demos. So first, who am I? My name is Windel Bouwman. I work at Demcon. I'm a Python and open source fan. I'm also working on another project, PPCI. Check that out, it's really cool. But it's not that useful as RustPython is probably. And here are some links.
Hi, I'm Xing Lu. I'm here working at the Zone as a software engineer. I used to work for Mozilla on Servo, Quantum, and Firefox. So, yeah, getting back to...
Okay. All right. So, I want to start with the RustPython project, a more overview. What is it? So, basically what it is, what you probably already guessed is, it's a Python implementation written in Rust. We are aiming at the Python 3 syntax. Homepage is there. You probably already know it. We have already 19 contributors now. The project is only running for less than a year, so it's still in very early phase. I don't know percentage, but I would say less than 5% of on par with CPython, I think. But the cool thing is that we already have a WebAssembly demo. Xing will show it. And there's not much of the standard library yet. So one may ask the question, why did we do this? One of the reasons is that I wanted to learn Rust. So going beyond an Hello World program, just straight on with a Python interpreter, why not? And Rust is of course safer than C, but you are here, so you know that. And also it's nice to learn about all the details of the Python interpreter. And the end goal would be that we have a Python interpreter which is safer than the CPython variant. So I will go into the more RustPython internals. What did we make so far and how does it work? So I will talk about which crates we have, the internals, compiler VM, how the import system works, and the built-ins. So this is the overall design. It's no different than CPython. So what it does is we take Python code, we lex it, then we parse it, we get an abstract syntax tree out, we compile that syntax tree to bytecode, we interpret it in a VM, and if we encounter an import command, we go in this loop again. Yeah, it's the same as in CPython, I would say. We have created some Rust crates. We have a RustPython parser, which contains all the going from source code to AST. And then we have Rust VM, which is the more runtime part. And then there is a Rust Python top-level crate, which combines the two. So this is how we split up the code. It's all in one Git repo as of now. I think that is better to keep it that way, but we'll see. So how does it work when we do the lexing part? Lexing in Python is particularly difficult because it's whitespace based. So it's hard to use a lexer generator because you have to keep track of the whitespace. So it is a manual lexer which just looks at all the characters and produces tokens. So the task of the lexer is take source code and get tokens out. And that's handwritten. Then we have a parser which is created with LLRPOP, LALRPOP. I don't know how you call it. This one will take the tokens and convert it into an abstract syntax tree of your Python source code. this actually works pretty well. And then we have the abstract syntax tree, which is the it's basically two Rust enums. I don't know if there's no code of that. What happens next in the phase is the compilation phase. We will take the abstract syntax tree, which we just parsed, and generate bytecode. And here you can see, for example, in Python you can use the this module. In CPython that is, because the this module we don't have yet in RustPython, but that will eventually be added. So here you can see an example of how a simple function in Python is translated to bytecode. So you see if you have a function which adds A, B, and 3, the bytecode will be load A, load B, perform an add operation, because the Python virtual machine is a stack machine. So how this works, it will load A on the stack, load B on the stack, perform an addition, saying taking two things off, doing add, placing the thing back. Then we will load the constant, then we have the result on the stack and the constant, and we do the add and return the value. The bytecode you see here on the right bottom is CPython bytecode. The bytecode is not standard, so in RustPython we have yet another bytecode. Why not? So maybe it's an ID. In .NET and Java the bytecode is standard, and that has some advantages. But in Python this is not the case yet. But maybe that will come. Then in the Python virtual machine, how we implement it in Rust, it is basically a big fetch and dispatch loop. So it will fetch a bytecode from the generated bytecode and look with a match statement, what is the bytecode, and perform the operation. And as you see here, if the bytecode is an import instruction, we will, as you remember, invoke the whole loop again. One interesting thing of Rust is that we have RC and refcell, and we benefited from that because in CPython there's reference counting, but Rust RC is actually a reference counting struct. So what we did is we defined a type PyObjectRef, which is a reference count to the actual object. So in this way we use the RC type in Rust to do the reference counting for us. And a PyObject, we define it as a struct with, it has a type, which is actually a PyObjectRef again, because a type is also a Python object. And furthermore, each object has a dictionary, so in Python you can set attributes and get attributes at will. So it's really dynamic. And then for some Python types we need to store internally some payload. So if you have a Python string, it's backed by a Rust string. An integer is now backed by big int. This was also nice, so we have arbitrary integer precision. And bytes is simple a factor of bytes. So that's pretty good. So this is an example of how we implemented the built-in functions of Python in Rust. Because in Python there's a lot of built-in functions, and in CPython these are implemented in C. But we of course have to implement them in Rust all over again. So this is an example of the all method in Python. I can show that in the demo later on. And here you see some the syntax of how you want to implement a function in Rust, which is then exposed to the Python world. So when this function is called, you will see that it has pyfunc_args as an argument, which contain all the positional arguments and the keyword arguments as they are in Python. And then there's an argcheck macro. So someone made a macro for this, which is very handy to check the types which you pass, because Python is really dynamic. But here we want to know what are the Python types of the the args you pass in this function. And then we perform the functionality of the all method, which is check if all the elements in an array are true or not. And then in the end we say return new bool. And since Python has exceptions and Rust has not, we created the PyResult type, which is actually, it's okay or it's an exception. So a function is either going okay or it has an exception. If it has an exception, this exception has to be propagated. So this really fits nicely on the Rust logic. Yes, demo time. All right. So if you want to run RustPython, you simply have to clone the repository and hit cargo run. All right. When you enter this shell, you will see, okay, you can do things like 2 to the power 200. Since we have big integer support, thanks to the big int Rust crate. That's also one of the good things of implementing this in Rust. We can leverage all of the Rust crates which are already there. So this was surprisingly simple to do. I don't know how they did it in CPython, probably a library. What can you do more? You can do list comprehensions, for example. So if you create a list like this for A in, this will work. What also will work is if A is, you can do, I think you can do this. If A is bigger than 1, for example. So most of the syntax now works. So the part that's now to be done is implementing most of the standard library. That's really a lot of work, and there can be a lot copy-pasted probably from CPython, and it will be a messy operation, but in the end it will probably work, but it will take time. And also some built-in objects are not yet complete, but syntax-wise I think it's pretty far. I'll have to go on. So why we picked the Rust room and not the Python room is because join us in making this project, because I estimated that it would be probably 10 man-years of work. So if I do this in my own, it will be finished in 2029. But maybe it's finished earlier, I don't know. And also some challenges are the Python dictionary. So in the Python, the dictionary, each Python object can be used as a key in Python. And what we wanted to do was to use the Rust hashmap for this dictionary. But the Rust hashmap has, you have to implement the equal traits and the hash traits in Rust. But the hash and equal function in Python return exceptions. And the equal and hash traits expect that the operation is always success. So we're stuck. So any ideas from you would be appreciated here. How we can solve this. So we're stuck there, so probably it will be a homegrown hash map implementation. And also the standard library is still a lot of work, and there's this project Ouroboros, which has a implementation of the standard library in Python. So I want to use that, but yeah, we'll see. So with that, Xing.
Cool. And besides the command line tool and the REPL, we also have the WebAssembly build. So since you're in the Rust room, I assume that you might heard about WebAssembly already. But just to quick recap, WebAssembly is a low-level assembly-like language definition and its binary format that's now intended to run in the browser, which can run at almost native performance. So it also works well together with the JavaScript. So if you have a web app that has some bottleneck, performance bottleneck, you can write that part in WebAssembly, make it really fast, and they still work together with the JavaScript. So Rust compiler already have the ability to compile to WebAssembly. It has all the toolset around it. Thanks to Ryan Little for helping us porting this to WebAssembly. He did most of the work. So the toolchain we used is the WebAssembly pack from the Rust team. They give you a WebAssembly ByGen tool that can generate the bindings between JavaScript and Rust. So you don't have to write everything yourself. And there's also the WebSys crate, which exposes the DOM API to you. So you can use things like console log, accessing the DOM tree, manipulating the DOM tree. And there's also it's all wrapped in the Webpack configuration, so you can run Webpack to compile everything. And we have a Travis CI pipeline that compiles the WebAssembly build, build a demo page, and then push it to GitHub pages. So this is a rough idea about the workflow. So we have one crate called RustPython WASM, which is the main crate for the WebAssembly build. And it imports, it uses the RustPython parser and RustPython VM, just like the command line one. And we introduced additional crates from the WebAssembly part, which is the WASM ByGen, which generates the JavaScript and Rust glue code, and the WebSys that give you the DOM access. And we have some demo page that's written in HTML, JavaScript, CSS, and they're all compiled with Webpack. Webpack internally will call WASMPack, which turns our Rust crate into a node module, an NPM module. So in our demo page, we can just use JavaScript import RP from that NPM module. And the whole thing will be compiled with Travis CI and pushed to our demo page. So to show you some, we cannot show all the code, but show some interesting part of it. So this is the main function we used in JavaScript to evaluate the Python source code. So the key part you can see is that there's a WASM ByGen attribute, and it gives us a JavaScript name called PyEval. So that means this Rust function will be exposed to JavaScript as PyEval. So in the JavaScript, we can just call PyEval and give you a string of Python source code. And internally, it will set up the virtual machine, parse it, and then execute it in the virtual machine. And this is from the JavaScript side. You import that NPM module, we compile from Rust, and then have the code in a string, and then just call rp.pyeval. We expose the rp to the global variable, so we can easily access it. And we'll talk about the standard out a little bit later. Yeah, so there are some concepts in Python that doesn't match exactly to browsers. So for example, Python print. How do you print something to a web console? So there are two ways we can do this. First, we map that to the JavaScript console log. So as you can see, we use the WebSys console. This gives Rust the ability to directly call console log. So inside this, we create a built-in function for print that calls console log. So when you call a print in Python, it will print to the JavaScript console. And for demo purpose, we also wanted to print a standard output to a HTML element. So this is quite complex, but you can see we still use WebSys. You can get the window, you can get the document, and you can use query selector, this all in Rust. And then you can set the value for that element. Cool. Let's see a demo. So here you will see we have a simple Python Fibonacci. And if you run it, the output will be here. We only print to 10 now. We can probably increase to 50. And you can see it runs pretty fast. Let's try maybe 100. It still prints pretty fast. And this is the one we use in the demo page, but you can use or directly call it from JavaScript. For example, you can call rp.pyval and then give it a Python code. So this will print to the standard output. We can try something like yeah, I'll print 2. So this is our thank you. Yeah, you can check it out. It's on our GitHub pages. And for the future step of the WebAssembly build, first, we can try to do some replacement for JavaScript. There's already some project like this called Bryson, but it's like trying to recreate Python completely in JavaScript. So they have some performance bottlenecks. But since we have the WebAssembly build, we can probably mitigate that performance hit. We can probably make a Python IDE in browser, or we can try to do a Jupyter notebook that runs completely in browser. There's something called iodide, which they compile CPython to WebAssembly and make a Jupyter notebook. So we can also try this with RustPython. So I can imagine that we have a lot of use cases in data science and all the AI-related stuff in the browser. Yep. So thank you. And this is our project page on GitHub. And you can also find our GitHub pages. So check it out. Yeah. Thank you. Yeah. Questions? Okay.
How big is the web page when you load it with the RustPython in it? It's another question, do you transpile the interpreter to JavaScript or to WASM? Or would there be another way to do it, just not to have to just transpile the bytecode to WASM? I don't know if it's clear.
Sorry, I don't get the last part. So you said now we transpile the Rust code to WASM, and
What you ship when you ship the WASM code?
Mhm.
What's in there? Is there the interpreter? Is there only the Python code?
yeah, that is the whole pass. Your question was when we ship that WASM build, what is in the WASM, right? So it's the whole parser in the virtual machine.
I could show it.
Yeah. Yeah, it's basically the whole parser in the virtual machine compiled into WebAssembly, and they have some using the WASM pack. They expose some of the APIs to JavaScript, so JavaScript can call it directly. Yeah.
So it's 2.6 megabyte. I think that was the first question. How big is it?
Oh yeah, this is the WebAssembly binary, and it's like 2.6 megabyte.
I was wondering if you have an extensibility story. So if you can extend RustPython with your own Rust code.
So the question was, how do you extend RustPython? In CPython you have the CPython extensions. In PyPy they did an interesting story that was CPyExt. So I think what that does is it mimics the C API which Python provides to extensions and couples that to PyPy. Probably we will do the same, but also I think we will have 2 extension mechanisms at some point. But none of that is there right now, so at this moment it's not possible, but I think that will come, that we will have a possibility for Rust extensions and a possibility to load existing CPython extensions as well. That would be great, at least to my opinion.
You're starting an
So the question was, if you start from scratch, is this a good opportunity to do sandboxing right and right? I didn't think about sandboxing, but if you look at the CPython code, it is a 20-year-old code base, so logically there's legacy there. So this is a good opportunity to start afresh, so to say. So there is some things in CPython which maybe not be nice. So yeah, I think we'll look at how can we make it in a good way, or in an improved way where we can. So probably it will not be 100% compatible then in the end with CPython, because we didn't implement some quirks, if you want to call it that way.
Sorry, to answer that again. Also, to be very honest, we are not like super like language experts, so we didn't think about, okay, if we start from scratch, we can get all these benefits. It's more like a learning experience. So we start from scratch because we want to learn both Python and Rust. So
Thank you very much. We are over time.